Mm-hmm. So thanks for the introduction and the opportunity to present our work here on acceleration mapping. And we wanted to do direct acceleration mapping in the human aorta at 7T and combine this with B1 shimming. So acceleration can be directly linked to force and therefore might be a potential relevant clinical parameter. And we can either derive acceleration vector fields from measured velocity data, or it has also been shown that we can directly measure acceleration with phase contrast MRI, and this has been done at lower field strengths. And it was also shown that phase contrast velocimetry profits from going to ultra-high fields because we just have that gain in signal-to-noise ratio. However, as we already heard before, going to these high fields also has some drawbacks, and one of them are B1 inhomogeneities, and these can prohibit correct velocity quantifications in area with really low B1, as seen by these disconnected streamlines here, where the velocity quantification just fails. So we aimed for direct acceleration mapping in combination with B1 shimming. And as I already said, we can derive acceleration data from measured velocity data due to the fact that acceleration is just the total derivative of the velocity with respect to time. And if we want to calculate this, we have to take the partial derivative with respect to time, but we also need all these terms here where we have derivatives with respect to all spatial coordinates. And from this, we can already see that in order to quantify acceleration based on velocity data, we need time-resolved, 3-directional, and 3D velocity data, so we need to have 4D flow data. And one disadvantage of this method is that by calculating all these derivatives, we will amplify the noise that we already have in the velocity data. On the other hand, we can directly measure acceleration using phase contrast MRI, and therefore we have to have a look at the gradient-induced phase, which is given by this formula where we have this integral over our gradient and the spatial coordinate of the magnetization. And typically, if we consider only velocity, we make a Taylor expansion of the spatial coordinate, and we end after the term which has velocity in there. And we can just take another term into our Taylor expansion, and we see that we can produce a phase proportional to our acceleration if we apply a second gradient moment. And to do so, we need a phase contrast sequence where we control the second gradient moment, and therefore we typically apply tripolar gradients because they give us enough degrees of freedom to do so. However, using these tripolar gradients, we additionally prolong the echo times, which also costs us some signal again. So that's why we moved to 7 Tesla, and as already mentioned in the talk before, here we have the problem of these B1 inhomogeneities, and we can overcome them by using PDX. And in our case, we have an 8-channel coil where we can modulate the phase and amplitude of each channel. So we have the same RF pulse played out on every of these coil elements, but in our case, we modulated the phase only. And to do so, we have to acquire the complex B1 maps of all these elements before our phase contrast measurements. And then we do an optimization where we minimize the coefficient of variation of the flip angle within a defined region of interest. So in our experiments, we first acquired velocity data and did this in a balanced 2-point fashion with a velocity encoding sensitivity of 1.5 meters per second. And this gave us a temporal resolution of 35 milliseconds. And due to limitations of our system, we were only able to acquire data in a single breath hold and use no navigator. That's why we could also only perform 2D acquisitions. And then we performed our acceleration measurements, where we kept the first gradient moment 0 and varied the second gradient moment in a balanced 2-point fashion. And corresponding to the velocity encoding sensitivity, we can then have an acceleration encoding sensitivity, which was 70 meters per second squared here. And on the bottom, you see an example of 2 consecutive TRs for such an acceleration sequence, where we alternate between these green and red gradients in order to encode the acceleration on the slice select axis here. And here you can see results from an example time frame in mid-systole. So first of all, we can see the measured velocity data here encoded in all 3 directions. And we calculated as a measure for quality the standard deviation of our velocity vector field in end diastole. And these results look quite promising. However, if we calculate acceleration based on these velocity maps, we can clearly see the noise amplification, and we see that we get quite poor image quality. In contrast, if we have a look at directly measured acceleration data, we can see that the image quality significantly improves, which can also be seen comparing the standard deviation in end diastole. And since we were only able to acquire 2D data, we were not able to calculate all these terms of this convective acceleration, and that's why we see some systematic differences between calculated and measured acceleration. We acquired this in a time-resolved fashion with ECG gating. So here you can see all 3 acceleration components over the cardiac cycle. So to conclude, we successfully performed direct acceleration mapping in the human aorta at 7 Tesla. We did this in combination with B1 shimming in order to gain a homogeneous B1 distribution within our region of interest. And the measured acceleration data shows significant improvement compared to the data calculated from our measured velocity data, which is partly due to the fact that we could only acquire 2D velocity data. And this direct measurement of acceleration now provides an additional hemodynamic parameter also at ultra-high fields, which might be beneficial in clinical situations. And with that, I'd like to thank you for your attention.